Okay, so now we're ready to think about finding the conditional expectation of one random variable conditional on another random variable. Okay? And in doing that, we're also going to see how conditional independence and independence are different things, how variables that might, in an unconditional sense, be dependent on each other, once we start conditioning on things, can become reasonably thought of as independent. So what we're going to do is we're sticking with our city council election random variable. And remember, X random variable was the location of the median voter on the city council after the election. But now we're going to add another election that's taking place in the same electoral environment. Okay, so we're going to add random variable Y, which is location of the median voter on the school board in that same town. Okay, and so we'll have the status quo on the school board. Again, we're going to think about there being 3 members of the school board and only one of them's up for re-election this cycle. So we've got person D here on the school board, person E, and person F. And we are going to assume that E is up for re-election. Okay. And if he wins, the school board median will stay where it is at y equals 1. And if he loses, he will lose to person E prime, who's kind of of the same ilk as A prime. Adding the numbers in there, we have kind of similar numbers. Person D's ideal point is 0, person E's is 1, F is 2, so that's a little bit different. E prime is 5 here. Okay. So Y is going to take the value 1 if E wins, and we'll move to 2 if E loses. And we're going to assume that Y is facing exactly the same electoral environment as Y is produced, I should say, by the same electoral environment as X is. Okay, so that the probability of Y, if there's anti-incumbent sentiment, Y staying 1 is 0.3, Y moving to 2 is 0.7, and the probability of Y conditional on no anti-incumbent sentiment would be 8 for 1 and 0.2 for 2. So I'm keeping all of the same probabilities, and just as we did before, we're going to assume the probability of anti-incumbent sentiment is 0.5. So what we want here is we want to find expected value of X. Okay, so remember X is the city council median voter, conditional on Y equals 1. Okay, so what are we saying here? Like we read in the newspaper, school board retains its left-leaning majority. That would be journalese for what we're saying, oh, Y equals 1 here. Given that we know that, what do we expect X to be? So this is kind of a learning thing. Given what we know happened in one election that's sharing the same electoral environment, what can we, how can we update our beliefs about the other one? Here, how can we use that information? So, okay, so we know how to do this. The we need here are the probabilities of X conditional on Y equals 1. And that's how all of this conditional moment stuff comes from, just making sure that we're using the probabilities that correspond to whatever environment we're thinking about, and the outcomes just are what they are. So what we need is these probabilities. Okay, and we know how to find conditional probabilities. That would just be the joint probability x and y, that x takes value either 1 or 4 there, and y equals 1. So it's the joint probability divided by the probability that y equals 1. This is just definition of conditional probability with values for y that we're thinking of here. And we'd find one value for x equals 1 and another one for x equals 4. And it's all looking fine, except here's where things get a little bit tough. Okay. How to find this joint probability? We're interested in this because we don't think x and y are independent. We think we can learn something about x by observing y. So we're not going to get this joint probability by multiplying the probability that x equals 1 and y equals 1, et cetera. We can't do that. So what to do? Well, here's where we can use the idea of conditional independence. It would be completely antithetical to the whole point of this example to assume that x and y are independent. The whole point of the example is that yes, that they're in the same electoral environment, and we see that y goes in favor of the left-leaning incumbent. That should tell us something about the likelihood that the same thing will happen with x. Okay, so we cannot assume that x and y are independent, but what might be reasonable to assume, since we've already modeled it out to some extent, is if we knew whether the anti-incumbent environment was present or not, that x and y are independent. Okay, so it's, even though we don't want to assume just basic independence, conditional independence seems kind of reasonable. That's what we're going to do. Okay, and so the answer here is assume x, y are independent conditional on knowing there's an anti-incumbent environment or that there's not one. Okay, that's what we're going to do. Okay. So the overall, what we're going to do is we're going to find these joint probabilities in 2 steps. We're going to find the joint conditional probabilities. Okay, so we're going to find the probability that x is 1 and y is 1 conditional on there being an anti-incumbent environment. And that's going to be easy because we'll just multiply the probability that x is 1 and the probability that y is 1 conditional on that environment. And we'll do the same thing for conditional on no anti-incumbent environment. Okay. So we'll have these pairs of joint conditional probabilities, and then we're going to use the law of total probability to put them together and find the unconditional joint probability, which is what we want right here, which is something that I've circled in every color I have. So that's where we're going. And before that, let me maybe write the steps over here. Okay, so find the x, y conditional on AI, and to do this, we're going to use that conditional independence assumption, and then we're going to find just plain joint distribution with the law of total probability. Okay. And that will get us our the numerator of the expression for the probability of x conditional on values of y. So, all right, let's do it. So let's see. What we're going to do now is find those joint conditional probabilities. Okay, it's quite a mouthful, right? So what I'm looking for is a joint probability. I'm looking for combinations of X and Y. So X can be 1 and Y can be 1, X can be 1 and Y can be 2, X can be 4, Y can be 1, X can be 4, and Y can be 2. Those are the values that you can take. And I want to find the joint probability conditional on the anti-incumbent environment and conditional on not that. And from that, see if I can write small enough to get it all, fit it all in here. I want to find the unconditional joint probabilities. So in each of these columns here, when I'm conditioning on the anti-incumbent environment, I can use that conditional independence assumption. I'm going to write here. Okay, we're assuming that independent conditional on AI. Okay. So if we know there's an anti-incumbent environment, then the probability that each of those incumbents is reelected is 0.3. So the joint probability that they both are, because in this world, they're independent, it's 0.3 times 0.3, 0.9. And sorry, 0.09. The probability that X is reelected, or say that A is reelected and X remains at 1 is 0.3, and E is not reelected, so that Y becomes 2, that is 0.7. I get 0.21 here. And the probability that the median on the city council moves to 4 and the median on the school board stays at 1 is 0.7 times 0.3. And the probability that we get 4 and 2 is the probability that X is 4, that's 0.7, times the probability that Y is 2, that is also 0.7, so 0.21, 0.49 here, 0.49. And let's just quickly make sure that those probabilities sum to 1, since I'm writing some weird numbers here. So I get 30 plus 70 does indeed equal 1. Okay. Okay. One of my joint distributions here. I'm going to do the same thing now using the probabilities that correspond to no anti-incumbent sediment. So in that world, they're both reelected with probability 0.8. Okay, so conditionally independent in that world, 2. Probability of 0.6. We get X equals 1 and Y equals 2 by multiplying the probability of each of those individual events, 0.16. Probability that X equals 4 times the probability that Y equals 1 is also 0.16, and the probability that X equals 4 and Y equals 2 is 0.04. Again, let's just check that those probabilities sum to 1. I get 20 plus 80 is 1. That's correct. All right. Okay, so the conditional independence is what we use to get this column and that column. Okay, so that is step 1. And step 2 is find the unconditional joint probabilities using the law of total probability. Okay, so using the idea that probability that xy equals whatever it is the probability of xy conditional on AI times the probability of AI plus for probability 1 conditional on not AI times that probability. So that's what we need to do here in our last column. So remember the probability that we're in that anti-incumbent world was 0.5. So here I'm going to take the joint probability conditional on AI multiplied by the probability that we're in that world times this number times the probability that we're in that world. Okay, so I get 0.9 times 0.5. Wrote it wrong again. 0.09 times 0.5 plus 0.64 times 0.5, that equals 0.365, another set of numbers that I punched out in advance here. So for the probability, the unconditional joint probability here, it's this times 0.5 plus that times 0.5. Okay, so the probability of the 1-2 combination in the AI world times the probability of the AI world plus the probability of the 1-2 outcome in the non-AI world is 0.16 times 0.5, and that adds up to 185 here. We have 0.6. Oops, hang on. There's a 0.16 here, but let's write it in the same order. We've actually got the same two numbers here, so it's going to be the same 0.5. Again, it's still 0.21 times 0.5 plus 0.16 times 0.5. And then the last one is 0.49 times 0.5 plus 0.04 times 0.5, and that equals, it's probability, Kathy, it can't be greater than 1, equals 0.265. And if we check, these numbers do sum to 1. Okay, those are the numbers that we need for the probability. This is the joint distribution of X and Y. That's what we need to calculate the probability of X conditional on values of Y. So let's go to a new page, copy this stuff in a more readable form, and get back to the main thing that we were looking for here. Okay. So what I did there was filled out my cross tabs. We would have X equals 1, or X equals 4, and Y could equal 1, or Y could equal 2. And the probabilities that I'm just recopying what I had on the previous page would be 0.365, 0.185, 0.185, 0.265 here. And if we sum across the rows or down the columns to get the marginals, we get 0.55 and 0.45, just as we found before. So that is reassuring here. Okay. So now getting back to kind of our main thing, what we want is the expected value of X conditional on Y equals 1. So for that, we want the PMF of X conditional on Y equals 1. So that's going to be X 1, 4, and we want PX conditional on Y equals 1 here. So that is, give myself a little bit more space here. It's going to be equal to the joint probability that X equals 1 and Y equals 1 divided by just the marginal probability that Y equals 1. And so I can just take those numbers right here from my, my crosstabs. Okay, probability that they both equals 1, that's my 0.365. And probability that Y equals 1 is 0.5 0.55. And that equals 0.664. Okay, so that's the probability that x equals 1 and the probability that x equals 4. Both cases conditional on y being 1 is joint probability of, supposed to be the mistake I'm going to make writing that time, the joint probability of x equals 4 and y equals 1 divided by the probability that y equals 1. So that joint probability is 0.185 divided by 0.55 here, and that gives me 0.336, and those also sum to 1. And could I have skipped this and just subtracted 0.664 from 1? Yes, I could have. There's the probabilities that I need. Now I can calculate those conditional moments. So let's do it here. Okay. Let's calculate expected value of x conditional on y equals 1 is x takes the value 1 with probability 0.664. Okay, so that probability, because these are the probabilities we use to calculate that conditional moment, 4 times 0.336, and what do we get for that? We get 2.01. And let's calculate the conditional variance while we're at it. The variance of x conditional on y equals 1. Remind ourselves that is the expectation of x squared conditional on y equals 1 minus the expectation of x conditional on y equals 1, that whole thing squared. So expectation of x squared, again, it's the same deal. It's just I'm being careful to use the probabilities that correspond to the appropriate conditioning event. So it's 1 squared is 1 times 0.664 plus 4 squared is 16 times 0.336. My conditional expectation of x squared minus the square of the conditional mean, which, where did it go? It's 2.01 squared, and that equals 2.00. Okay. So this is like kind of an example of the great power that thinking about conditional probabilities in the context of random variables gives us. We can work through these problems. We need to do a little bit of modeling in the sense we needed to think about the role of the anti-incumbent sentiment here, but often that's what's motivating our analysis in the first place, is wanting to make those arguments that we're capturing in models. And overall, what we did to find the conditional mean and the conditional variance is we needed to find the joint distribution of x and y. And we couldn't do that just by multiplying the probability that x was 1 and y is 1, because the whole point of the exercise was that we did not think that x and y were independent. But if we found a way to talk about what made them not independent, this anti-incumbent sentiment, and model that out so that we could find the joint distribution conditional on anti-incumbent sentiment and conditional on not that, then we could find those probabilities and use the law of total probability to put them together, find the joint distribution, from there calculate the conditional distribution here. And again, just to emphasize what we did here, it was different than what we did in the first lesson in this unit, is that here we are conditioning on another random variable. Okay. In the notes, I work through the conditional moments for the other case, the case of y equals 2. It's the same process here. I think I'm not going to do it in the video. It's like exactly the same process, but that's the example here. And again, sort of touching base with some of the ideas that I opened this unit with, everything we're doing here is stuff that we sort of already knew how to do. We already knew how to think about joint and conditional probabilities. We already knew how to find expected values and variances. We're just putting it all together. And there's nothing actually hard about it. It's just there's a lot of possibilities to keep straight, okay? And in particular, you get joint distributions that may or may not themselves be conditional distributions. In my view, this is not really, it's not really right to say that the conditional probability framework is complicated. It's not. It's a framework that allows us to manage the complexity of the real world. And again, that's one of the things that social scientists love about probability. So I've got one more little thing to tell you about conditional independence in the next lesson. I probably got other things I want to tell you about conditional independence later on in the course, but one more in this little chunk here. So I'll see you then.